start. Thank you, Michelle. I'm going.
Can you see that now?
Hang on, wait. Coming. Perfect.
Yep.
Very good. Yep,
okay.
It's lovely.
Awesome. Okay, good afternoon. So today we're going to focus on inheritance and taking a family history. So we're going to go slowly through taking a family history so you can have a practice, and then I'll do a little bit of population genetics at the end. And then if you want to do more and have more practice, I think there's a lot more exercises available on the Kura Cloud case study. So at the end of the session last week, I went through the different types of inheritance. And so I've summarized in this table some key features. So in terms of the Mendelian inheritance patterns that we encounter with the rare types of inheritance, we have autosomal dominant, and some clear features that help you to recognize that a condition is autosomal dominant is that you get clear transmission through multiple generations, and that males and females are equally affected. And that if you have an autosomal dominant condition, there's a 50% chance or a 1 in 2 chance that you will pass that on to your children. So as a child, you have a 50% chance of receiving an autosomal dominant trait from your parent. Issues that complicate autosomal dominant inheritance typically would be reduced penetrance and variable expression. So this is that whole idea that we all have a different genetic background. So a trait in one individual may not manifest in the same manner as it does in another individual. So it may be masked or appear less severe to a certain extent. With autosomal recessive conditions, if you're looking at typically at a multi-generation family, you would only expect one sibship to be affected. So you wouldn't see many cases within a 3-generation family. If there are multiple cases, this would suggest that it's probably not a recessive trait. Again, males and females affected equally. Typically, you would see increased frequency of recessive conditions if there's parental consanguinity. So if there are families, particularly if they, for religious or other reasons where there is cousin-cousin marriages or other types of consanguineous matings, then you may see an increase of recessive conditions. With recessive conditions, obviously you can be a carrier and not be affected. So that's a big issue with recessive conditions is then potential for carrier testing. Because if you have 2 carrier parents, then obviously there's a risk of 1 in 4 of having an affected child. X-linked dominant, we don't talk about that much because they're quite rare or very rare, but with an X-linked dominant condition, this would be a trait that's transmitted from females to both their sons and daughters. So it's on the X chromosome, and males can only pass it on to their daughters because obviously males pass on their Y chromosome. So you can't get male to male transition. With X dominant conditions, both sexes are affected, but girls are often more affected than boys, and some conditions are just completely lethal in males, which is why you get the disparity. With recessive X-linked conditions, typically males are affected, and this is because women have that backup chromosome. So because women have 2 X chromosomes, and we have random X inactivation, in terms of dosage, with a recessive condition, women are normally okay because they have the backup X chromosome. So things like color blindness, hemophilia, etc., are X-linked recessive conditions, and you don't get male-to-male transmission again because it's on the X chromosome. With mitochondrial inheritance, this is only transmitted by females, obviously, because all the mitochondria originate from the egg cell, not the sperm. So in a family history or in a multi-generation pedigree, you would typically see transmission of a trait through the maternal line only, so through the females. And this is where the mitochondria is coming. Typically, these are in conditions that are high energy requirement conditions because of the mitochondria are affected. Again, they're pretty rare, but both sexes are affected. And we talked about this last week, that males typically may be slightly more affected with some conditions. Maybe that's to do with heteroplasmy, and maybe that's to do with hormonal differences as well. And the other type of inheritance pattern you may see in family histories is where there's a chromosomal abnormality. So last week we talked about translocations, and that you can transmit something like a Robertsonian translation in multiple generations. And if the individual themselves is a balanced carrier, then phenotypically they're normal. And so you can then have these families where there are increased risks of miscarriage, increased risk of stillborn babies, increased risk of abnormalities, because there's a much higher instance of abnormal chromosomes being distributed in meiosis. So again, a family history where there might be multiple generations of increased miscarriage and stillborns could be indicative that there may be a familial translocation chromosome that's passing through the family. So this is, again, just kind of like some key facts. If you have different members, affected members in different generations, not going to be autosomal recessive. Affected members in one sibship probably is going to be recessive. Parental consanguinity, probably recessive. Males affected, probably X-linked. More females, X-linked dominant. Male-to-male transmission won't be X-linked because obviously there's no X chromosome involved here. So it'll be either Y-linked or autosomal dominant, more likely. And if a male has no affected descendants, then you might want to think about whether or not it's a mitochondrial inheritance. These were the true-false questions. So just think about it in the other way. A lot of you don't need to learn much in terms of family histories and pedigree analysis, because a lot of it's kind of just like logic problems. You just got to work back from what it is that you're talking about. So again, as I said, male-to-male transmission suggests mitochondrial inheritance. Well, this would be false because if we have male-to-male, we talked about it's either autosomal dominant or Y. With mitochondrial inheritance, we're talking about going through the maternal line. With parental consanguinity, autosomal recessive, yes, because you're decreasing the gene pool, so increasing the likelihood of rare alleles coming together. More females than males suggests X-linked dominant, yes, but it's very, very rare. More females than males, mitochondrial, no, so you'd expect equal numbers. And father to son, X-linked dominant, again, no, it would typically be autosomal dominant or Y-linked inheritance. So there's some getting used to the symbols. I mean, a lot of them we don't typically use. Obviously, we need like the squares and the circles for males and females. Often if you see a number in it, it means it's kind of laziness on the part of us. So we just kind of say, oh, there's 5 boys or there's 3 girls. It saves writing out lots of squares or circles. A stillborn often has a line through it. Sometimes it's written as a smaller square or smaller circle, or sometimes if it's or sometimes that only applies if it's miscarriage. You see sometimes a smaller square or circle written. When you're taking a family history, you have a proband. So that's kind of like the origin of the person with the disease that's presenting, and then you kind of build the pedigree around the proband, and that person normally has an arrow pointing to them. And then there'll be lots of other symbols that we encounter, but if you don't know the gender, kind of it's a diamond shape, and there's things like if someone is adopted, there's brackets around it, and we'll talk about these if these come up as we go through. Why do people get referred to genetic counsellors or genetic consultants? Mostly for diagnosis of a condition. So if you wanted confirmation that a patient had a genetic condition, you'd refer them to explain or confirm a diagnosis. Implications of a family history. So there could be implications in terms of taking specific actions with your health, particularly if it's something to do with a cancer risk, maybe. Discuss diagnostic pre-symptomatic tests for a genetic condition, again, similarly. Also, in terms of recessive conditions and carrier testing, it's quite important if there is an instance of a genetic condition. So people might want to discuss their risks and reproduction options in terms of whether or not they're going to have prenatal diagnosis or pre-implantation genetic diagnosis. And for some people, it may be really important because there may be increased risk for of a personal or family history of a cancer. So it comes with a whole load of ethical, legal, social issues, as we would expect. So obviously you have women's reproductive choice, the autonomy of the child versus the mother, in the implications for someone who's going to undergo pre-implantation genetics or prenatal or postnatal diagnosis. And then we have issues such as the cultural responsiveness of healthcare services in relation to genetic testing. Are people aware? Are they informed when they're consenting? Is it in line with their beliefs? Also, health inequity is a big issue for us in New Zealand in terms of who has access to genetic and genomic testing. Less of an issue possibly for us, but it's still important factors are potential for discrimination based on genetic information, although this can happen by proxy in terms of legal and insurance. So there's that whole issue. If it's something is recorded in a patient's notes, then they want to seek health insurance, and if it's been recorded that they've had a genetic test and have a family history of a genetic condition, then that's something then effectively they have to declare, or it can void their insurance. in terms of if they don't disclose genetic testing results. And obviously there are implications for other family members as well. So if somebody has a genetic test and they find out they're a carrier or they're at high risk of a particular condition, that obviously has implications then for the family members who may not want to have had testing or to have had that information. So there is quite a whole lot of issues surrounding people getting genetic information it's important to be aware of. Okay, so we're going to play around with drawing some family trees. The full paper that this picture is taken from, the reference is here, and in the Kura Cloud lesson 2 that Diane has given you access to, all of this information is up, so you can go through this in slower time if you want later on. So if you've got a pen and paper with you, we can go through and you can just practice doodling as we go through this. So we're just going to do the family tree, and in our case, the proband is the 2-year-old boy called Justin. And he's the son of Michael and Sarah, and he's been referred to us because of multiple congenital anomalies and developmental delay. So if you want to sort of start by, when you've got pen and paper, you can draw that little family unit to start with. And the first step that we would do if we're going to ask somebody about a family history, we want to ask about sibship. So we want to find out whether or not Justin has any other brothers or sisters. We need to then find out about his parents. We need to find out more about Michael and Sarah, whether or not they have siblings, something about their parents. And all of the time we want to know about whether they're alive, whether they're deceased, and whether they have any known medical conditions. And so then the aim is then to extend the pedigree to include 3 generations, so at least up to grandparents. And then we have to also ask difficult questions where we're asking about potential consanguinity and any other relevant information that, about any distant relatives. So again, making sure that we're knowing kind of where possible age of death, if they are deceased, and also what conditions are prevalent within that 3-generation family. Okay, so you should have a little diagram like this. So we have the proband here, this is the child, and we have mum and dad. And so the couple then tell you they've got another healthy son, John, who's age 6. So you can add this to your little family now, and he's healthy. And they tell you they also had a previous pregnancy that resulted in a miscarriage. Michael, the dad here, this is Michael, also tells you he had a previous relationship where he had a pregnancy. Well, he didn't have a pregnancy. His partner had a pregnancy, and that resulted in a stillborn daughter. So we can add that now to this first stage of the family history. So again, in this, what we're doing here is we're finding out whether the parents have conceived other pregnancies, either as a couple or with other partners, and what the outcome was. And again, key issues obviously are being sensitive when you're talking to people and mirroring the language that they use. And obviously, you know, if they're with other partners or other relationships, there can be issues that are uncomfortable or maybe difficult to broach. So it's just really important to be responsive to how the patient is giving you information. Okay, so we should have something like this. So here we see his Michael's previous relationship that resulted in a stillborn baby. So it was a girl that died, and so they put SB for stillborn, and the line through it means that they're deceased. And we also see here that we have the healthy brother, this one here, who's a 6-year-old. And then we have this little dot here, as I referred to before. Some people manifest a miscarriage as a little dot. So then we need to find out more about Michael and Sarah's siblings, whether or not they have had children and whether or not they've also lost pregnancies or had any difficulties, and also about their parents, whether they're alive, whether they're well, what issues there are. And then start then asking about unusual family illnesses or unusual illnesses in anyone else. And that's when we want to start to see if there's any clustering in the family of diseases. So in this case, Michael tells you that he has a sister, and his sister has no children, so we can add that in. His parents also had a stillborn daughter, and his mother is alive, but his father is dead. So we can add that to the family pedigree. In terms of Sarah, she has a brother and a sister. Her sister has 3 children, 1 daughter and 2 sons. So you can do that lazy notation for the boys if you want. You can do a square with a number 2 in it. And Sarah's parents are both alive, and her father was adopted. So we're just trying to give you as many different variables as we can for this one. Okay. So this is what your family history should look a bit like now. So here you can see here we've got the 2 boys and the girl. So here's our original family. So here's our proband that we started with, and we've got Michael and Sarah. We've got Sarah's brother and Sarah's sister. Sarah's sister has 3 children, 2 boys and a girl. And this here says is Sarah's father, who's adopted. So this bracket around the square suggests that her father is adopted and that both parents are alive. In terms of Michael, we can see here that his parents also had a stillborn child, so here, and his sister has no children. This funny little arrow thing here suggests that means that she's had no children, and we can see here that his father is deceased and his mother is still alive. So now we want to go back to a bit more information about the grandparents, about the parents' siblings and the offsprings of the grandparents. And it's also potentially we want to try, if possible, to know a bit more about the age of death, the known cause of death. So obviously when we're talking about cancer, if we're looking for a family history of cancer, anybody who's died relatively young, potentially under the age of 60, suggests that there could be a genetic component. So cancer at a younger age suggests a stronger genetic component. So knowing the age of death is really important. So if there's a family history where people are dying quite young, then it could be suggestive of an increased risk for a particular type of cancer. So you find out that Michael's mum has a brother and he has no children, and that both of her parents are dead. Sarah's mum has a brother. He has 4 children, 2 boys, 2 girls, and Sarah's mum's parents are both dead. So we can add that in. So that would then give us that final, that extending the pedigree to the final generation. So now we have a 3-generation family history. So it looks quite nice. We can see that obviously in generation 1, these grandparents are all deceased. But we've got a little bit more information here. So if now we've got this pedigree, so we've got this 3-generation pedigree, we've seen that there are at least 3 children where we've got the proband and we've got 2 stillborn. And we've got another child here that's died age 3. We've got a stillborn, and we've got the miscarriage as well. So the presence of 3 children with multiple congenital abnormalities would raise suspicion that there's a chromosomal translocation. So as we talked about those ones last week, where the people who are holding the translocation, if they're balanced, they're okay. But if they transmit, when they're making gametes, sometimes they may be unbalanced. So that may mean that when that egg or sperm is fertilized, you may have a resulting embryo that has a wrong number of chromosomes or abnormal number of chromosomes, which means there's a much greater chance of having a miscarriage or a stillbirth, depending on what the extra or missing chromosome is. And so other things that we might want to ask in this family, maybe not be of much use in this family, but other questions that you could ask are about potential consanguinity between Justin's parents, because it looks like it's coming through this side here. And if there's any other information that might be of particular interest in more distant relatives. Obviously, for a lot of people, when you're taking a family history, if you're talking about family members that have died or there are issues, then there's going to be, you have to be very sensitive, particularly if there's areas of non-paternity or concealed extramarital relationships. And that's something else that is quite important now, that becomes up a lot when people refer to like mum or dad or auntie or uncle, actually clarifying whether these are biological relatives, because often in many cases they wouldn't be, or they could be step parents, or they could be people they've grown up knowing as mum or dad, but aren't actually a biological relative. And sometimes if you're taking a family history from somebody, they may not realize, because they see someone as a relative, they may not realize kind of the importance medically of actually whether or not someone's a biological relative in terms of family history. So that's quite important to establish that people are actually their biological relatives. And so it's also important when doing this to be tactful and as such. And I think people also need to be reassured that confidential information about their family, including relationships and issues with family health, is very much confidential, and that it doesn't get shared without consent. Okay, so here's one that you can just practice. This should be a quick one to draw very quickly. So obviously it's a made up syndrome. But here we've called it unicorn syndrome. So young adult onset condition, presents as a golden bone structure from the skull. Autosomal dominant. So if you can just sketch out the pedigree now. So this is your, so pretend this is your family. So your paternal grandfather has it, his wife didn't. Your father has it, his sister didn't. Your father married Jane. You have 3 siblings, 1 brother, 2 sisters, and one of your sisters has the unicorn syndrome. So again, it should just be a nice, quick way of just writing out a pedigree. Okay, so that you should have a nice drawing, and it should be a clear autosomal condition where you've got 3 generations essentially with an affected individual. So if you want more practice of family history taking, as I said in the second CuraCloud lesson that Diane has made available to you, you can skip past the bit where I'm telling you all this stuff. And then there's 3 recordings of case histories from a UK genomics website, and you can practice taking a family history there, where you can, they're interviewing a patient, and you can practice taking a family history and then comparing it to what the person has done in the actual example. So it's relatively straightforward. And so the rest of the session, I just thought we could focus a little bit on some population genetics. And then if you have any questions about inheritance or population genetics, obviously come back to me and we can go over any of those as well. So I quite like population genetics because it's kind of like the math bit of genetics. And so it's used sometimes when we want to try and work out frequency of a condition in a population. So with a lot of rare conditions, we can't tell by looking at someone whether they're a carrier of a disease. So if we understand how many people are affected from a condition, we can use this formula to work out how many people we'd expect in a given population to be carriers. And if we can have an understanding of how many people we expect to be carriers of a particular condition, we can have understand a better idea of a risk in a population. So population genetics is kind of just the math side of genetics. It's working out likelihood of different genotypes in a given population. And when we talk about population, we mean a local group of the same species that has the potential to breed. And their gene pool then is all the alleles that reproductive population have. So when we talk about allele frequencies, we do a simplified equation where we have P plus Q equals 1. And these are your 2 alleles. So if you're talking about, eye color and you've got big B, little b, these are the 2 alleles that make up your genotype. And so they have to total 1. And so P is the frequency of one allele and Q is the frequency of the other. A genotype frequency then is really the 3 genotypes that you have. So if you have 2 alleles, like a dominant and a recessive allele, you're going to have 3 genotypes. You're going to have the double homozygote dominant, the double homozygote recessive, and you're going to have the heterozygote. So you've got your 3 genotypes. So because we have 2 alleles and we have 3 genotypes, again, we can use this maths to work out what the relative genotype contributions are of a particular condition in a given population. So we have a second equation that we use. And in this case, it's P squared plus 2PQ plus Q squared is 1. And in this equation, the P squared is the frequency of one homozygote, the Q squared is the frequency of the other homozygote, and the 2PQ represents the heterozygotes in a population. So by plugging it, by knowing So what is useful for us is by knowing the frequency of recessive condition people, or people who have a recessive condition in the population. For example, we said this is either p squared or q squared. We can then work out what p is and what q is from this equation and this equation, and then we can use that to work out the frequency of carriers in a population, which can be quite useful sometimes. So that's kind of what we're going to work on in the next 10 minutes or so. This is just showing you why we use these equations. So basically, if you have sperm and eggs, so your sperm can either have, if you're heterozygote, you can have either allele, you can have a P or a Q. And similarly, an egg that's heterozygote can have either allele, the P or the Q. And then when they come together, you can have P by P, which is P squared. You can have P by Q, which is PQ. Q by P, which is again PQ, or Q by Q, which is Q squared. And this derives us our genotype equation where we've got P squared, and we've got two PQs, these two here, and we've got Q squared, and that all has to add up to 1. So that basically says that all the genotypes can only be one of those 3, and the alleles can only be one of those 2. And obviously with some conditions, they're much more complex, but essentially these are the two basic formula that we use in population genetics. So the first thing is just to get familiar with calculating allele frequencies. So a lot of this is just counting. So in this instance here, we're using the example of a variant or polymorphism in the CCR5, which is a receptor for HIV. And we have two alleles, the 1 allele and the delta 32 allele. And in this case, we have the 3 genotypes, so double 1 homozygote, delta 32, and the heterozygote. And we have 3 phenotypes that we'd expect that correlate to each of the genotypes. So for the majority of people, they would have the 1-1 genotype. They'll be homozygote for 1-1, which is like the common genotype in the population, and they'd be susceptible to sexually transmitted HIV. And in this case, we've got a genotype frequency in our population of 100, with 79 people have this genotype. We then have heterozygotes who have the 1-1 allele, and they also have a delta 32 allele. And in this case, they're susceptible to sexually transmitted HIV, but they have a slower progression to AIDS. And in our population, there are 20 individuals. And then we have a final genotype, which are the homozygotes for delta 32. And these individuals are resistant to sexually transmitted HIV. And in our population of 100, we have 1 individual who has this genotype. So because we have a population of 100 people, that means we have 200 alleles, because everybody, we're talking about a gene on an autosome, everybody has 2 alleles, one from mum and one from dad. So all we do to calculate genotype frequencies for each of these genotypes is we're going to count the alleles. So first of all, if we want to know the allele frequency of allele 1, we count up. So we have 158 1 alleles. So there's these that comes from here. So these guys all have 2 lots of the 1 allele. So this is the 158 that come from here. Plus we have 20 alleles coming from the heterozygotes, where they've got 1 allele that is the 1 allele. And so that means in this population of 100 individuals, we have 178 out of the possible 200 alleles are the 1 allele, which gives us a frequency then of 0.89. So in this population, the frequency of the 1 allele, the dominant allele, is 0.89. And then if we work out the genotype frequency of the delta 32 allele, we count that we have 2 coming from here. So this 1 individual has 2 alleles that are delta 32. And then there's 20 alleles we have here from the heterozygotes that have half their alleles that are delta 32. So that means in this case, we now have 22 delta 32 alleles out of the potential 200, which is 0.11. And obviously, because P plus Q equals 1, these 2 add up. So if you trust the genetics, you didn't need to calculate the genotype frequency of this. You could just subtract 0.89 from 1, and which also gives you 0.11 as the frequency of the minor or the recessive allele. And that is your entire gene pool for this particular genotype. Okay, so you can have a go at this one. I've changed the numbers to make it easy, so you can do it without a calculator, so I can do it without a calculator. So the same phenotype, same genotype, I've just changed the genotype frequency so you can work out what the alleles are. Okay, so did you get 0.7 for the frequency of the one allele? Yes, and delta for the delta 32, 0.3. So basically for the one allele, it's 50 plus 50 plus 40 over 200. And for the delta 32 allele, it's 10 plus 10 plus 40 over 200. So you have 0.7 and 0.3. So also that just shows you how like we calculate and how in different populations, you'll have different genotype frequencies, which because you'll have different allele frequencies in different populations, depending on the how common that particular variant is. Okay, so given those two equations and that information, we now can answer questions like this. So for example, if we know that 9% of an African population is born with a severe form of sickle cell, and we want to find out the population, the percentage of the population that's going to be more resistant to malaria because they're heterozygote, we can use these equations to work out how many heterozygotes or what the frequency of heterozygotes is going to be in our population. So in this case here, our 9% in this population is the same as p squared. So if we want to find out what p is, we do the square root of 9%, which is 0.3. And so now we know that p is 0.3. We know that q is 0.7. So if we know what p is and we know what q is, we know that the heterozygotes are going to be 2 times p times q. So in this case, that will be 2 times 0.3 times 0.7, which equals 0.42. So we'd expect in this population, 42% of the population to be heterozygote and more resistant to malaria. So individuals who are heterozygote are more resistant to malaria because the sickling of the red blood cell makes it harder for the parasite to infect. So if that was okay, you can do the next one.
Sorry, where did you get the 0.7 from?
Oh, sorry. So because we know what p is, which is 0.3, we know that p plus q has to equal 1. So we know that q then has to be 0.7 because we know that 0.3 plus q has to be add up to 1 because that's our gene pool in this case.
Oh, perfect, thanks.
So for the phenylketonuria one, it's the same kind of principle. Again, I've picked a number that's easy to square root because I can't square root hard numbers. It's the same kind of thing. So in this case, if we have 16% of the population are the recessive phenotype, so they are p squared, say, then we know that p is the square root of 16, which is 0.4. And so then we know if p is 0.4, we know that q has to be 0.6 because we know that p and q have to add up to 1. And so now if we want to find out how many carriers we have in our population, we know from the other equation that the carriers are 2 times p times q. So we know in this case, there will be 48% of our population would be carriers. Okay, does that kind of make sense? I've got some other ones that we can do just before we go. Okay, so this is kind of getting into where I'm at. So it's normally in my house, it's apocalypse or cats. So here we've got a scenario. So we've got, it's the apocalypse and we're in Wellington. So for us, my plan with the kids when the apocalypse happens and the zombies take over is that we're going to go to Soames Island, which is a little island near where we live. So we built this scenario based on this apocalypse scenario. So apparently the apocalypse has happened and you and 19 friends don't fancy your chances sticking around mainland Wellington, so you build a raft and sail to the island and start a new population. And you're totally isolated from the rest of the world, and you're going to be the future of humanity. However, on arrival, you're not alone. There are 2 Siamese and 3 Persian cats that have also made it to the island, and they were carried on driftwood. They are the first cats to live on the island. All 5 cats have normal ears, but one carries the recessive allele for F, for folded ears. His genotype is F, big F, little f. As you're starting up a new community, you're concerned about your chances of winning future cat competitions to be held on the island, and you want to know the likelihood of a cat being produced with folded ears. So again, in this scenario, we can calculate the frequency of the big F and the little f allele in the cat population using the P plus Q equals 1 equation. And then what we're going to do is you're going to work out when the population gets to 100, how many genotypes you're going to have of each of the genotypes. And again, we use the other equation for that. So you can have like a couple of minutes to work that out if you want. So the first thing that we know is that we have 5 cats. So 5 cats means 10 alleles in total. And we have, of these 10 alleles, we have 1 small f, the folded allele, and we have 9 big F alleles. So we have a frequency of P and Q of 0.1 and 0.9. Doesn't matter which way you call them P and Q. And so from this, we can work out the frequency of the 3 genotypes. So if we say that P is 0.9, say, if that's the F, the big F, then we can work out the frequency of the those homozygotes by its 0.9 times 0.9, which is 0.81. So that's your kind of normal looking cats. If we say that the Q, the recessive allele, is 0.1, we can work out the genotypes for that. So that would be 0.1 times 0.1, which essentially is about 0.1 still. So there's probably about 1 cat that's going to be the other recessive phenotype with the folded ears. And then the heterozygotes will be 2 times P times Q, which is 2 times 0.9 times 0.1, which is 18. So you'd have 18 carrier cats. So you'd have 18 carriers, 81 normal homozygotes, which kind of makes up like that 99. And you'd probably have your 1 cat that would have your folded ear allele. Does that kind of make sense? Okay. And so now we're going to get into the breeding of the humans, not the cats. So, oops. So now you've done your ear aesthetics, you're going to focus on the human population. So we're assuming that the mainland population you survived was in Hardy-Weinberg equilibrium. It wasn't a weird recessive population, or it was a randomly mating population. So and that your friends weren't relatives or anything, they were all able to be part of a random mating gene pool. And so what you find out is that 2 of your friends are carriers for the recessive condition cystic fibrosis, and they both have the same variant, the delta F508. So if you're a homozygote for delta F508, then you have cystic fibrosis. So your friends are just carriers, but you don't know who of the 20 are carriers. So assuming that the frequency doesn't change as the population grows, what will be the incidence or the instance of cystic fibrosis on your island? And when the island population hits 100, how many people do you expect to have cystic fibrosis? And then if cystic fibrosis births on the island, you want to find out how many, whether they're going to be more frequent on your island now compared to on the mainland pre-apocalyptic times. And so I've given you a rough idea of what the current frequency of births in New Zealand is at the moment. And again, a few more minutes to work that one out. Okay, so in this case here, if we've got 40 total alleles, because we've got 20 people, then we know 2 of them are alleles for cystic fibrosis. So 2 out of 40 is 0.05. And so that is CC or P squared is 0.05 squared, which will be 0.0025. And if we multiply that by 100, it's about a quarter of a person every 100, so 0.25% of the population would be born. 0.0025 is 1 in 400. So in terms of the frequency on your island compared to the frequent on the mainland, it would be much greater. So on the mainland, we're saying that the frequency of cystic fibrosis is about 1 in 3,500. And if we're saying in your new population that you founded that has those 2 individuals who are carriers, the instance from that population from a limited gene pool then would be much greater. So it would be about 1 in 400. And that's kind of essentially what happens in a population with a limited gene pool. You're going to have a much higher incidence of a recessive condition. So I think that's probably all I was going to go through with population genetics. Obviously, there's loads and loads of questions that you can do, but I think if you know, as long as you know the basics, often the questions with population genetics is working out what the carrier frequency is and just understanding those 2 equations and how they relate to the different alleles and the different genotypes, which can be quite useful to do. And in terms of the family histories and working out the inheritance patterns, again, just trying to methodically work through what are logical relationships of all patterns of inheritance in a family history is often the easiest way to understand the transmission of a trait. Do you have any questions on those sort of things? I haven't got really anything else I was going to do today, but I can prepare stuff for next week's. Next week I was going to focus on cancer and maybe some genomic tests if that's relevant, but if I'm also open to questions for topics that you'd like me to cover next week, so please just put it either to the chat, or if you can either do it now, or you can send me an email later of any other topics that were genomics related you'd like covered. If there's anything specific to genomics and eye pathology, then let me know. Otherwise, I'll probably focus more on cancer next week. Diane, is there any other questions, do you think?
Michelle, sorry. There is a series of different things that are on our learning outcomes, I guess, for genetics. Yeah. And we don't really get clear history of what kind of questions have been asked for genetics because they're MCQs and they're not published, but they do cover a lot of things that I've had a bit of difficulty studying and stuff like that. So lots of different things like Sanger sequencings on the learning outcomes and the LOD score, and blood grouping enzymes, RFLPs, VNTRs.
Okay.
So that's all on our learning outcomes.
Okay.
But I'm just not quite sure how they'd ask MCQs about that kind of stuff, but it is on our
okay.
Our
So
list of things.
Maybe what I can do next week, I'll see if I can find some MCQs that cover those kinds of questions, and we can just explain what they are. And I think there'll be a limit to what sort of questions they can ask you on those kinds of topics. But if I'll find some questions and we can spend half the session next week going over some MCQs that cover those kind of topics, then hopefully that will be useful. And I'll definitely talk about the sequencing LOD scores. I don't think they'll ask you about LOD score anymore, but I can go over that quickly and sort of
quickly. 2 seconds.
That's fine. Yep. No, I can definitely do that next week. Yep. Is there any other topics? So that they're on your list, doesn't it, on your learning outcomes, and I can find some MCQs via Diane
to chat now.
I put the curriculum into the chat just so you can have a look as well, Michelle.
So unfortunately, we can't get access to past MCQs because they're all in a top secret MCQ bank.
The ones that I did have some, I think I've seen some, maybe they're not for the same exam, but I think you let me see some MCQs, don't you, Diane, that I can base next week's session on some of those.
Yeah.
Yeah.
Good. Okay, so here we go. So Michelle, I think that's you finished for the day.
Okay, I'll come back. So next week, cancer, molecular methods, and a whole load of MCQs we'll go through. Yeah.
Great.
Awesome. Okay. Enjoy the rest of your day. I'll head off and make sure my children are okay.
Yes. Yes.
Thanks, Michelle.
Okay, great. So Amanda, so I think what's next is there might be an exit survey. Is that right? And then we'll talk about homework.
You know the thing, something similar, something different. It's just reflecting on our A/B test a little bit further. And turn your video off, go off and do that.